This conference will now be recorded.
Hello everyone. Today we'll start with problems, and these two problems based on the discussion that we have already done in the last class, that is related to structural isomers of alkanes. And once we finish this, we will continue the nomenclature and isomerism of alkane, which we have already started in the last class. And after that, we will see preparation of alkanes, different methods for preparation of alkanes. The question says, what is the number of moles of carbon atoms present in n moles molecule of alkane if it exhibits 3 structural isomers? So there is n moles of molecule of alkane given. Now which alkane, that is not important, but suppose there is alkane and n moles of alkane is present. Now the number of moles of carbon in that particular alkane, that we have to find, provided it exhibits 3 structural isomers. Remember, in the last class we have seen that starting from the first member of alkane, the first member is CH4, then the next member is C2H6. So in this way you can move, that is gradually you can increase the number of carbon. So just take the example of methane. When you have n mole of methane, the number of carbon is also n, because per methane molecule you have just 1 carbon atom. Similarly, if we have n moles of C2H6, you will have 2 moles of carbon, isn't it? If you take the next member, which is C3H8, then there will be 3n number of moles of carbon atoms. So the question is basically asking, what is the which member of alkane where there is 3 structural isomers possible. So it is asking in a different way, indirect way, not directly it is asking that. So here we need 1 mole of, if we have taken n of this, we will have n moles of carbon. In this case, we will have 2n moles of carbon. So in this way, we can proceed. Okay. Now the next member, you can say it is 3C3H8, and here also we have 3n moles of carbon. But is it the correct? Because 3n is also present. It is starting from 3, then 4, 5, 6. So these two not possible. But 3n, is it possible? Because see, it is not possible because C3H8, no isomerism possible. The isomerism first starts with C4. That is the member where 4 carbons are present. So when it is C4H10, then you can have the first, that is, you can have structural isomerism. So this detail we have discussed in the last class. So when it is C4H10, you can have the simple one, which is N-butane, or you can have this one, which is isobutane. Okay. Now this is giving only 2 structural isomers. Now if you consider the next member, which is C5, so just add, remember the formula, it is CnH2n plus 2. So if it is 5, then it means it will be 12. 5 into 2, 10, plus 2, 12. Now for C5H10, there is basically 3 structural isomers possible. All of this we have already seen. This is the first one, that is the possibility. Now the next possibility is if it is isopentane. And the third possibility is this one. Fine. So that is why it means this will be our correct answer. So if you have n moles of C5H12, there must be 5 moles of carbon atoms. So 5n should be the correct answer. Okay. Next question. This is also related to structural isomers of alkane. Identify the molecular formula of an alkane. 4 formulas are given that exhibits only 2 different structural isomers. So the same thing we have just discussed in the previous question. In case of C4H10, you have already seen 2 structural isomers are possible. That means this should be the correct answer, right? And for C2H6, no structural isomerism possible. For C3H4H8, no structural isomerism possible. For C4H10, 2 possible. And when it is C6, now total 5 structural isomers possible. And you can also check in the previous class where all these 6 structures are drawn. So here we have a table. Number of carbon atoms 2, 3, 4, 6. Options A, B, C, D. And these are the corresponding alkane. Number of isomers not possible 2, and then 5. So this should be the correct option. That is C4H10, right? Okay, just let me check. It is exhibit only 2 different. Yes, C4H10 should be the correct answer. Next, we'll move to nomenclature and isomerism of alkane, which we have already started, but we will continue this. Isomerism we have already seen, but what about nomenclature? So if we talk about nomenclature, the detailed rules we have seen in the unit 12, basics of organic chemistry. Rules we have already discussed. Now, based on those rules, we will just discuss some examples of alkanes. That is, we'll take some structures and we'll try to write the name based on those rules. So suppose I'm drawing this molecule CH3, CH, CH2, CH3. So this is the molecule we have taken. Now we have to first find the longest chain that is possible, right? So this is alkane. There is no doubt in that. There is CC double bond, no CC double bond or triple bond. So there is only saturation. So numbering we will start from 1, 2, 3, 4, 5. Now why we are starting the numbering in this way? Because if you do the reverse numbering, suppose you have started the numbering from 1, then 2, then 3, then 4, and then 5. So if you are following the green one, then the substituents, that is the methyl substituents, their positions are 3 and 4, these two. But if you are following the red one, now you will see the methyl substituents that you are getting. The first substituent you are getting this one, which is at position 2, and the second substituent you are getting, which is at position 3. So that is why the red one numbering we will choose, not the green one. So the name of this will be, longest chain is 5 carbon, so it will end with pentane, but we have 2 methyl substituents at 2 position and 3 position, so the name will be 2,3 dimethyl pentane. Okay. Next structure we will see. Here we have CH2, CH3. Now we will proceed towards this side. So the first thing that we have to do is to find the longest chain that is possible. We will start from this side. 1, 2, 3, 4. Now don't move downward, because if you move downward, you will get 2 carbon. But if you move left hand side, you will get total 7 carbon. So it must be ending with heptane. But what about the substituents? We have substituents at 2 position, at 3 position, and we have also substituents at 4 position. 2 methyl substituent at 2 and 3 position, 1 ethyl substituent 4 position. But why the reverse numbering is not done, that is why I have not started the numbering from left hand side to right hand side, because if you do so, you will get the position for ethyl, which will be at 4, and the position for the 2 methyl will be 5 and 6. So 4, 5, 6, it is obviously not correct. We have to move from that side where we are getting first the substituents according to the first point of difference rule. So that is why the name will be here 3 substituents, but it will end with heptane. That is okay. But what will be the substituents? Ethyl and methyl. Now E will come first before methyl. So that is why you have to start with 4 ethyl. Then we have 2, 3 dimethyl, and then heptane. Okay. Next one. So next we will do the numbering. Now, if you simply, it is not that the parent chain, it will always be in the horizontal position. No, that is obviously not the, that is not the case always. It may be in the downward portion, or it may be in the upward portion. You just have to recognize it, right? So numbering will start from this position. Now, if we do so, we are getting substituents, methyl substituent at 7 position. We have ethyl substituents at 4 position, and we have 2 methyl substituents at 2 position. Okay. The same logic why we have not started it from the left hand side, because if we do so, it is true that methyl we will get at 7 position, but if you consider the other 2 substituents, you will see where it is not according to the first point of difference. Okay, so that is why we will choose this one. So here the first substituents you are getting at 2 position, then the next substituents you are getting at 4 position. Fine. So the name will be total 3 methyl substituents and 1 ethyl substituents. Ethyl substituent it is at 4 position. 2, sorry, this is not substituent, this is part of the parent chain, only 2 substituents. 2, 7 dimethyl octane, because total 8 carbon atoms in the parent chain. So 3 examples we have seen. Now one more example. Here we have now branching compared to these three examples that we have already discussed. Here branching is to some extent high, and also the parent chain, look at this, it is total 10 carbon. So here we have substituents at 3 position, then 4 position, then at 5 position we have ethyl substituents, we also have propyl substituents. Okay, then again at 7 position we have methyl substituents and we have ethyl substituents. So total number of ethyl substituents at 5 and 7, and methyl substituents we have 4 position, 7 position, and 4 position, 7 position. Yes, and then there is also 5 position, there is a propyl group. Okay, so 1, 2, 3, 4, 5 and 6. So here the name we are having, we have ethyl substituents, we have methyl substituents, we have propyl substituents. Now E, M and P. So alphabetically E should come first, after that it should be M, and then at last there will be propyl. Now the substituents for ethyl, here we have, which is at 5 position and also 7 position. These two. Then methyl we have 3 position, 4 position, 7 position. So 3, 4, 7. And for propyl only 1 3 carbon chain substituents at 5 position. So that is why this will be the numbering. But ethyl we have to write first, total 2 ethyl groups. Then it is methyl 3, 4, 7 and 5 propyl. Now total number of carbon is 10. So that is why it will end with decane. Okay, so here total 4 examples we have discussed based on the rules that we already have finished in the unit 12. Next, we'll also do some examples, but this time the nomenclature will be for some complex compounds. So it is for some complex compounds. Now, what I mean by complex compounds? So in this case, we will have some branching, but the branching, it is compared to the previous 4 cases. Now the branchings are comparatively more complex. So in the substituents, in the previous case, what we have seen, there is simple methyl substituents, ethyl substituents, propyl. Everything is that is linear chain substituents, but within substituents there is no branching. But now we will see that in the substituents also we can have some branching. That is the difference. But before going to that, here just have a look in this table. When you have methyl substituents, it is fine, and up to the next one, then next one, then next one. So okay, for these 3 there will be only common name, because branching is not possible here. But when you will come to 3 carbon like this is also propyl. But if it is linear chain, it is simple propyl. But when there is branching like this, so this is the branching, this is the connection point. Now you have to call it isopropyl. But this is basically the common name. If we actually want to use the proper IUPAC, then it should be 1 methyl ethyl. Now why it is called in this way 1-methyl ethyl? Because see, it is branching, that is true. But within branching also you have to do further numbering. So this is the connection point. This carbon is the connection point. It is connected to some larger molecule. This is the substituent part I am talking about. So the connection point should be having the number 1. Then this is number 2. You can also use prime so that you are not confused with the actual numbering in the parent chain. But whatever it is, now at 1' position you have methyl. So that is why it is 1-methyl ethyl. Okay. Similarly, when you will have 4 carbon, it is simple linear chain. So there is no complexity. But suppose the 4 carbon chain, if it is like this, look at these carbons which are in bold, that is actually the connection point. So when you have 4 carbon and the connection is like this, so this will be your number 1 carbon. Okay. Then we will have 2 carbon. This is 3 carbon. So this is the connection point, and in the connection point, one side there is ethyl group, another side there is methyl group. So obviously numbering will be the longest chain 1, 2, 3. But this methyl is the methyl group here. So that is why it is common name is secondary butyl, but actual name will be 1-methyl propyl. And here you have to mention it within first bracket because you will use this term ultimately in the IUPAC name of the whole molecule. So when you will use it, it should be within first bracket because after all this is a substituent. Next, these 4 carbon, another type of connection point may be there. And this is CH2, then, so this is the carbon with which it is connected. CH2, then CH. So see, now it is different. So numbering will be like this. And now it is 2 position methyl substituents. Try to understand the difference. This one is 1-methyl propyl. This one is 2-methyl propyl. Okay. Or isobutyl, common name. And the last one. This is connection point is this one. This carbon with which the whole molecule, actual molecule is connected. So this is 1 position. Now numbering, if you do 1 and 2, these 2 methyl, they are present at 1 position. So common name is tertiary butyl, but IUPAC name will be 1,1-dimethyl ethyl. 1,1-dimethyl, this part is ethyl. Fine. Now we will take example. The first example we are going to take. So see, here branching, it is not so simple. There is a molecule compared to the previous example. Now there is more branching. Numbering will be started from here 3, 4, 5, 6, 7, 8. So this is the longest chain, fine. And at 4 position, now 2 ways you can do the nomenclature. Suppose I am writing option 1. So in option 1, if you use the common name, though that is not exactly according to the IUPAC, but you can also get this type of name. You can also see somewhere. So that is why I am discussing both the options. 4, 4, because at 4 position you have 2 substituents and both the substituents are basically isopropyl substituents. Look at this. Isn't it isopropyl substituent? So 4, 4 di isopropyl, and total number of carbon in the longest chain is 8, so it will end with octane. 4,4 diisopropyl octane. So this is the one way you can do it. Another way, which is the following the exact IUPAC. Now the name will be 4,4. Now we will use this term 1-methyl ethyl. So within bracket we will write 1-methyl ethyl. But now we cannot use di. You have to write bis. Fine. So remember, when we are using it within bracket, we can't use di. Now it will be bis, and then ending is as usual. It will be ending with octane. Now we'll go to the second example. So numbering we will do, there will be total 9 carbon. Sorry. Now at 5 position, okay. Now the numbering will be 1, 2, 3, 4, 5. So this is symmetric, that because both side of 5 carbon there is 4 carbon. So whether you number this side or this side, it doesn't matter. But if you are increasing the numbering, that is after 5, if you are moving in this way, then it is ending at 8. So it is not the longest chain. So that is why the previous numbering is basically correct. So this part is basically the substituent part, right? Now within this part, we have to again do numbering. You can use prime, but I am here using different color so that the two numbering difference we can understand. So this is the connection point, this CC bond, right? So this should be number 1 carbon, this should be number 2 carbon, this should be number 3 carbon. Now when we have done it, you can see that at 1 position you have methyl group, at 2 position also you have methyl group. So this should be 1,2-dimethyl propyl, right? Now we will actually write the name at 5 position within bracket 1,2-dimethyl 1,2-dimethyl, and in the longest chain, that is this part, there is basically total 3 carbon. So it should be propyl. After that it should be nonene, because total number of carbon in the longest chain is 9. Fine. So two examples, one number 2, next number 3. So longest chain you can easily understand, and here longest chain should be starting from this side, because if you start from the right hand side at 4 position you will not get the first substituent, you will get the first substituent at 5 position. So that is why this numbering is correct. 6, 7, 8, 9. So at 5 position we have ethyl group, which is simple, there is no complexity. But at 4 position we have this tertiary butyl group. But if tertiary butyl group is fine, but if you actually follow the IUPAC nomenclature, now it will be different. So remember, in the previous table we have seen tertiary butyl, but actually following the exact IUPAC it will be 1,1-dimethyl ethyl. So at 5 position ethyl, 5 position ethyl, and at 4 position there is 1,1-dimethyl ethyl. Now the question arises, which one we should give priority? At a first glance it seems that E should be having more priority than M. But when we have this type of complex substituents and you have written the name within first bracket, now the M is not considered. Here D is considered. So that is why this substituent we have to write first. So this is the only difference from the when you have you are doing nomenclature for complex compounds while deciding the alphabetical order. That is, you have two substituents. In the previous two cases, this question doesn't arise because we do not have two substituents. But now we have two different substituents. And in one substituent, we have complex group. So that is why we are giving priority to D. Then at 5 position, ethyl. And it should end with nonene. Go to the next example, which is number 4. So you can understand these two parts are actually the substituent. So this is one part and this is one part. So for simplicity, suppose I'm writing it as A and this is as B. So if I'm doing the nomenclature from the left hand side to right hand side, that will be wrong, because in that case the first substituent you will get at 5 position. So that is why this side 3, 4, 5, 2, 3, 4, 5. Okay, actually both are having same position. So it is, that is the two substituents, they are at middle position. So whether you start numbering from left to right or right to left, it doesn't matter. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Both are giving you 5. So 3, 4, 5, 6, 7, 8, 9. Now for numbering within the complex substituents, that we will do it with different color. So it will be 1, then it is 2, then it is 3. So this is the longest chain of the complex substituents. So these two should be treated as substituents. Similarly, in the B part, number 1, number 2, number 3. At 2 position, you have methyl substituents, right? Now the name for A part, which is basically 1,1-dimethyl. 1,1-dimethyl longest chain propyl. So this is the A part, and the B part is 2-methyl propyl. So D is getting priority, so it will be at first position. Two-methyl propyl. Okay, and this is 5. So both are at 5 position. There is no such problem. So this is for A, and this is for B, and it is not end complete yet. You have to end it with non-end. So we have discussed 4 nomenclature for 4 alkanes with very complex substituents. So more you will practice it, your idea will be clear. Here D is getting more priority than methyl. So that is why it is written first in the IUPAC. 1,1-dimethyl propyl, and the second one is 2-methyl propyl. Both are at 5 position. Now we will start preparation of alkanes. So alkanes we can prepare. You can start from unsaturated hydrocarbon. You can start from alkyl halides, or we can also start from carboxylic acids. So when it is unsaturated hydrocarbon, that means we will start with alkene containing C double bond C, or we can start from alkyne containing C triple bond C. So this will be our starting material for the preparation of hydrocarbon. That is alkanes basically, because now our discussion is centered on alkanes. First point, unsaturated hydrocarbon. So alkanes can be prepared from alkenes or alkynes. And how? The first discussion we are going to do by the addition of hydrogen in presence of some catalyst. Now this catalyst may be nickel, it may be palladium or platinum. So all the that is metals that we are using for catalyst, they are basically from D block in the periodic table, right? And this reaction is known as hydrogenation reaction, because in this case you are adding hydrogen to CC double bond, so not triple bond. So now CC double bond and triple bond will be converted to CC single bond. So that is why you have to add hydrogen. So addition of hydrogen, hydrogenation, and the reverse process is called dehydrogenation. So just for information, you can now understand, if you consider the reverse reaction, that is when you are removing hydrogen from alkane by dehydrogenation process, that is also a procedure for the preparation of unsaturated hydrocarbons, right? So that we'll also see when we'll discuss in some other class the preparation methods of alkenes or alkynes. So here PT and PD, that is platinum and palladium, these two catalyze the reaction at room temperature. But if you take nickel, now you have to give more temperature. So take very simple alkene, which is the first alkene, ethylene, and in presence of nickel, Now the temperature should be high, centigrade, or alternatively, if you take PT or PD, now it will be room temperature. And what you are getting? 2 hydrogen atoms will be added to these 2 carbons, and that is why ultimately you will get similarly. If we start from alkyne, this is the first main member of alkyne. Here we need 1 mole of H2 is enough for 1 mole of ethylene, because 2 hydrogen atoms you are getting from a single molecule of H2. But in this case, here if you add 1 hydrogen molecule, you will get H2 ethylene. But then again, if you add 1 more, then only you will get CH3, that is ethane. So in this case, 2 moles required. The mole ratio is different. Now the same, whatever you have used here, so I am writing here 2, and then we are getting CH3. So this is the method for preparation of alkane when the starting material is unsaturated hydrocarbon, that is alkene or alkyne. This is A, this will be B, and this will be C. So probably we'll be able to finish alkyl halides today. So B is alkyl halide. Alkanes can be prepared from alkyl halides by these following 5 methods. Total 5 methods we'll discuss. The first one, reduction with hydrogen. So obviously, hydrogen atom will be added. But this hydrogen atom, that is the source of hydrogen atom, it is not necessary that you have to use directly hydrogen molecule. In the previous case, you have used hydrogen molecule directly in the presence of some metal catalyst. But now it is not that, it is not like that. Here we will use some reagents which will basically produce hydrogen atom or nascent hydrogen, which is expressed in this way. So if you take any of this mixture, fine, then there will be production of H atom, which is written in this way, and that will be replacing the halogen, because now our starting material is alkyl halide. In general, you can write it like this. So this X will be replaced by RH. So this is alkane, this is alkyl halide. Now this process is not for alkyl fluoride, because to break RF bond, it is really difficult. So that is not possible. So it is only for except fluoride, other halogens are okay. So other alkyl halides can be converted to alkane by reduction with hydrogen in presence of any of these following reducing agent. Okay. So these mixtures will produce hydrogen. Example we can take CH3, CH2, CH2Cl. So this is propyl chloride in presence of, just take the first reagent, it is written in this way or sometimes with a plus sign, and above the arrow within third bracket H. That means it is basically producing hydrogen atom or nascent hydrogen. And this chlorine is now replaced by this H, and your product will be 1 more hydrogen. So basically it is now CH3, right? So zinc HCl, zinc acetic acid, zinc copper couple in ethanol, zinc with sodium hydroxide and lithium aluminum hydride. This is a very good source of hydride ion. Okay, so very strong reducing agent. So any of these reagent will do the work. Now the second one, total 5 methods are there. In the second one, this is basically a name reaction. So based on the name of the scientist, Woods, we have this reaction, Woods reaction. Obviously, the starting material is alkyl halide, because that is the heading under which we are discussing these 5 methods. So a solution of alkyl halide in dry diethyl ether, which is the solvent. Diethyl ether means ethyl group, oxygen ethyl group. In short, it is written as Et2O. Treated with sodium metal. So here reagent we are using sodium metal. And remember, in this method, you are not just getting any alkane, it is always a symmetrical alkane that you are getting. That is the unique nature of this reaction. Why it is so? When you will see the mechanism, it will be clear. A symmetrical alkane containing double the number of carbon atoms present in the alkyl group is formed. That means the starting alkyl halide that you have started. So suppose you have started from CH3Cl, and here another molecule of CH3Cl we will take, and these two parts will be removed and these two parts will be connected. That means the final product, it is always that is total number of carbon, it is double the amount of the initial. So in general way, if I write that Rx, another Rx, as if these two R is now connected, so product is RR. Fine. So that is why it is always double the number of carbon compared to the reactant, that is compared to starting material. In the product, number of carbon double. And this method is specific for producing higher alkanes. So you are basically getting higher alkanes. You have started from suppose CH3Cl and now you are getting C2H6. So you are getting some higher alkane with higher number of carbon. But it is always even number of carbon. Symmetrical, even number of carbon. And it has to be because you are just multiplying the number of carbon. So it will always be even. And why we do not take, if the question is arising in your mind that why we are not taking one CH3Cl with another CH3CH2Cl, but that we cannot take, and why it is so, we will also discuss the reason. But before that, just see the net reaction. This is not the mechanism, this is a net reaction. You have taken two Rx molecule and in between these two sodium metal is retained so that you can easily understand what is actually happening. So here X, X and 2Na removed, and these are as if connected with this. So you are getting RR and 2NaX. Now X, if it is Cl, you are getting 2NaCl. Now the actual example is also mentioned here. If you have started from CH3Br, two molecules, in the middle if you place sodium, now we will get two molecules of sodium bromide as byproduct, and this will be your final product. Similarly, the next example, we have taken ethyl iodide, two molecules. So you are getting symmetrical and even number. Total number of carbon is 4 here. Total number of carbon is 2 here. So it is always even number. Though here it seems very simple that RR is connected and 2NaCl is 2NaX is removed. But if we want to know the mechanism is basically radical mechanism. So you may get question that Wood's reaction is based on radical mechanism or ion. So it is radical mechanism. What is happening here? Sodium metal, we know it is a source of electron. It can give electron. Set means single electron transfer. So a single electron will be transferred from sodium, oxidation state 0. And this single electron, if you simply do homolysis, so Rx bond, if you break, not heterolysis. Heterolysis means it will be R plus X minus like this, but it is not that. So R with one electron, X with one electron. Now this R dot that is produced and X dot. Now this X dot, if it is taking this electron from sodium, the fate of X dot will be, now it will be X minus, and that X minus will be combining with this counter ion Na plus, because after sodium has already sacrificed one electron, now it is already converted to Na plus. So this Na plus can combine with X minus. Now come to R dot. This R dot can take from another sodium another single electron transfer. Now it is becoming R minus and R. And counter ion we can have Na plus, because in the medium we have this is only positive ion Na plus. And this is another Rx molecule, and R minus is attacking Rx from the back side, and this type of mechanism is called SN2 mechanism. Now details of SN2 mechanism, that is substitution by molecular nucleophilic, that is actually done in separate unit. But this is a mechanism for substitution reaction where nucleophile attacks the starting material, which is alkyl halide, from the back side. Why I am saying backside? Because X is leaving group here, and the attacking reagent R minus is as if the nucleophile which is attacking this R from the backside, and X is removed. So again we are getting NaX as byproduct, and this is the final product we are getting. Now related to these reactions, we will discuss some limitations. So some limitations are there. You can already see the limitations that you cannot make unsymmetrical alkane, and there is always even number of carbon. So why it is? That is the question. So drawbacks of Woods reaction or limitations of Woods reaction, you can only make symmetric alkanes, not anything else. Then why we cannot make unsymmetrical? The reason is, if you take two different alkyl halides to prepare unsymmetrical alkane, now there will be odd number of carbon. So we can take simply CH3Cl, and you can take another CH2, CH3, CH2Cl, and obviously in presence of sodium. Now the question is here, all the three possibilities are there. Methyl will connect with, it can connect with another methyl. So that is the R group of another CH3Cl. So in that case, you will get this. Their CH3 can connect with this one. Now this is our desired product. But another, that is CH3CH2, it can connect with another CH2CH3. Now you can understand it in a better way if I take Rx and suppose this is R prime X, because this is not just true for these two, any different types of starting material if you have started. So what difference you have done here? You have not started from two molecules of CH3Cl or two molecules of CH3CH2Cl. You have started one of this, one of this. That means you have started with Rx and R prime X. So as if this is RR, this is RR prime, and this is R prime R prime. So you are basically getting two extra product. You only, this is the desired product, but these two are extra we are getting as byproduct. So when we are doing so, to prepare unsymmetrical alkane with odd number of carbon, here carbon number is odd, 3. These two are even, 4, 2, 3, 4. A mixture of 3 alkanes actually produce. So this is the problem we are facing here. So we cannot prepare it. That is unsymmetrical. If the alkyl halides be bulky in nature, especially at the halogen end, that is the carbon with which halogen is attached, if there is some branching, or if it is bulky, there is greater amount of alkene produced. But we are not trying to prepare alkene. Our purpose is to make alkane. But if alkene is produced, that will be wastage of the starting material. But why alkyl halides with bulky nature, especially at halogen end, we are facing this problem? To understand this, just take this example. Suppose our starting material is CH3, CH2. See, there is some branching. Okay. So from this, the radical that we will get is something like this. Now what will happen? As this is a bulky, so it will always have a tendency for disproportionation. Now what I mean by disproportionation? Just write another same molecule, that is same radical. So same radical I have mentioned, but instead of writing CH3, if I write here H, so what will happen? Just to get eliminate from this bulkiness, this H, there will be homolysis, and this H will be now removed as H dot. So and here we will have some carbon dot. Now these two can connect and it can make alkene here, and these two can connect, it can make sorry, it is not CH2, it is CH. Fine. So this is disproportionation, because see, one molecule is sacrificing H dot, another molecule is accepting H dot. So the freight of this will be, now it is converted to alkene propene basically, and this one will be converted to CH3, CH2, CH3. So you are getting this alkane, though this is not the alkane you are, sorry, what I mean to say, if you are using Woods reaction, what we do, we take Rx and from 2 Rx we get RR. But here what you are getting, from starting from this, you are getting this type of alkane, which is not the alkane that we normally get from woods. It is a different type of alkane. And another product you are getting alkene. And that is because of the disproportionation of this R dot. Disproportionation. After this, we are getting two different products. So this is a problem we face if we take alkyl halides with bulky nature, especially at halogen end. This method also fails if you take tertiary alkyl halide. Now, what is the problem with this? Just look at the previous table. See here, R minus is produced. That means if you start from with tertiary butyl halide, so there will be X, but instead of writing X, I am writing here negative charge. Now this negative charge over carbon, this is a very good base. Now this base, it can remove hydrogen from another tertiary butyl halide. So this is another molecule of Rx. So this negative charge, it can capture hydrogen from beta position of carbon. So beta position means this is alpha position with respect to S, and all these positions are beta. Now the beta position, any of these hydrogen, there is total 9 beta hydrogen. One hydrogen I am writing in this way. Now this can take this hydrogen and this CH bond is broken. Okay. So this CH bond is broken, and what will happen? It will make CC double bond here. CX bond will be removed. So ultimately what we are getting? We are getting CH3. This is the alkane we are getting. And from this part we are getting alkene. So this is also another type of disproportionation reaction that we have just. So the ultimate point is bulkiness should not be there, whether it is tertiary butyl halide or this type of halide. It is always better if you can take linear type of chain. So these are the drawbacks, and the last drawback you can easily understand, you cannot make methane because it is always the connection of two R groups. But if you want to make methane, what will be your starting material? Because it is already having a single carbon. But Wood's reaction is connecting two carbon and you are getting double amount of carbon. But that is not possible for methane. So that is why methane you cannot make by Wood's reaction. Fine. Now these drawbacks of Wood's reaction can be, there is alternative method for it. And that method is Corehouse method. So in Corehouse method, what is the difference? Obviously now the reagents are different. One reagent is always same. That is one starting material under which we are discussing all this method. This is number 3. 1, 2 we have finished. This is number 3. One of the starting material is always alkyl halide, but the other reagent is something like this, R2CuLi. It is called lithium dialkyl cuprate. The reagent name is Gilman reagent. So this is one starting material, another starting material is alkyl halide, that is R'(X). So one R group will come from R2CuLi, another R group which we are calling it as R', that will come from the alkyl halide. And what you will get? You will get R'. So this is the reaction. Lithium dialkyl cuprate, it remains like this. So lithium is as if the positive counterpart. So negative charge will be from this part. Now this R, one of this R group is connected with this, we are getting R'. And these are the byproducts, alkyl cuprate and lithium halide. So side products are RCu and lithium halide, LiX. Now this is general reaction, but next we have seen actual example. So in this case, ethyl group is our R group, isn't it? And this is our R'. So when these two are connected, here we are getting 2 carbon, here we are getting 3 carbon. So total number of carbon will be 5. So 5 carbon we are getting. And all these two, there is no branching. So the final product is always linear. This is ETCU, which is this one. LiX is LiBr. Now, how we can prepare the Gilman reagent? That is the next question. That is how you can prepare lithium dialkyl cuprate. So for that, you have to start from alkyl halide and lithium. you will get first formation of organolithium or alkyl lithium. Organo means the alkyl part, we are calling it as organo because it is organic part, and lithium, RLi. Now this RLi, next it will react with this salt which is copper bromide, and you will finally get Gilman reagent, which we also call it as lithium dialkyl cuprate. So overall charge is negative, which is balanced by this lithium plus. Next, this Corehouse reaction, we can use it to prepare both symmetrical as well as unsymmetrical. So it doesn't matter. Now the previous problem that we have faced in case of Wood's reaction, that is overcome. You can make both of them. It doesn't matter. And here R group in the alkyl halide that you have taken, that is R prime basically. I can write it R prime here. It should be something like this. Benzylic, this is methyl. Benzylic means CH2PH. It can be allylic, that means CH2 CC double bond. It can be 1 degree any group. It may be cyclic 2 degree. That means suppose this type of something cyclic, this is obviously 2 degree. If this is the connection point, that is if the halogen is here, the carbon with which X is attached, this carbon is secondary because it is connected to 2 more carbon. But it is cyclic. But why not normal 2 degree? Because if it is normal 2 degree, so you will get to any other groups. Now it will add more bulkiness. But here, as this part is connected, the steric problem will not be so high. But these two, as they are freely present, so more bulkiness will be there. So that is a cyclic 2 degree alkyl. Aryl, though we are not discussing here any aromatic compounds, but you can also do the reaction with PHX. That means halogen attached with benzene ring, PHCl, PHB, that also you can do. Or alkynyl group. Alkynyl group means the halogen is attached to CC double bond and there may be hydrogen or R, whatever. So these are the different types of groups that we can take. But if you take tertiary butyl group, that will create problem. So what is the problem that we will face if you take tertiary butyl group? In the previous case also we have seen if you take tertiary butyl halogen, we are facing some problem. So suppose I have taken 3-methyl group with some halogen, and this methyl group I am writing it like this. Now the problem is here this R, that is Gilman reagent, if you consider, which is something like this, and then lithium plus is the counter ion. Now this R group, it is basically present as R minus. So this R minus, because see, it is carbon metal bond. R group is some carbon metal bond. Obviously metal will acquire the positive charge. R side will be the negative side. Now this R, it will act as R negative and it will capture this H. Ultimately this CH bond will be broken. It will make CC bond, X will be removed. So you will be getting some alkene, but that is not your desired product. So this is the problem that we will have to face if we take tertiary butyl group. So only this type of groups, as it is mentioned here, that is methyl, benzylic, allylic, only this type of groups are preferred. Then only there will be no such problem. From Grignard reagents, that is the fourth method, that also we can make. In the previous case, alkyl halide is one of the reactant and another reactant is Gilman. Now in the fourth method, alkyl halide is one of the reactant, obviously, and the second reagent is Grignard reagent. Just like Gilman reagent, we have again taken some reagent. So alkyl halides react with Mg in the presence of dry ether as solvent, and in this way we can get Grignard reagent. In general, you can call it alkyl magnesium halide. Alkyl are magnesium, then halide. Now in this case, Mg is basically the positive part because it is metal, and these two sides, though I am not saying it is completely ionic compound. So we should not write it as NaCl. NaCl, how you can write? It is Na plus Cl minus. It is not like that, but R and X, these two parts, compared to the metal, obviously more electronegative. That is carbon and halogen. They are more electronegative than any metal. So that is why there will be some negative charge over R and X. So this will have 2 plus charge. So RMgX you have started with, you can take CH3Mg or ethyl Mg. You are treating it with halogen. It may be ClBrI, not fluorine. And that is done in presence of dry ether. It must be moisture free because this reagent is very moisture sensitive. Fine. So RMgX will be produced in this way, and that is called Grignard reagent. You cannot take alkyl fluoride because they are not very reactive. Breaking carbon fluorine bond is difficult. So they are not used. Now the carbon atom of this alkyl group, that is we are talking about the carbon atom of this alkyl group, which is directly attached to magnesium metal that acts as carbanion. Now the reason I have already said, carbon is more electronegative than metal, so obviously this part will be carbanion. This reagent is basically organometallic reagent. Organometallic reagent means where you have some carbon metal bond. So here also you have carbon metal bond. So this will be carbanion because carbon is more electronegative. Now Grignard reagent readily reacts with compounds where we have some active hydrogen. So that is why I am saying if you take any of this molecule, that is where active hydrogen is present, your purpose will be served. So R minus will react with some compound having active hydrogen and ultimately it will produce RH. So here you can see the examples. This is our RMgX. This is the R part. It will take H from H2O. So that is the reason during the preparation of Grignard reagent, we are making it water free, dry ether, because in the second step we will do the reaction. If you at the first point, if we are having this, that we cannot make Grignard reagent properly, right? So water which is having active hydrogen, you can get CH3, CH3, which is nothing but C2H6. So here you have CH3, CH2, it is capturing one hydrogen, you are getting CH3, CH3. And the fate of the other side product is, as H is taken from water, OH is left. Now Mg as it is 2 plus, so one side as if there is OH, another side there is Br. Similarly, this is the active hydrogen present in carboxylic acid. And this is the R part, it will take it, it will produce methane. This is the fate of the rest of the part. Sorry. Similarly, you can also do it. Suppose I am writing it here, CH3MgI. You can take some alcohol. So in alcohol also there is active hydrogen, it can take it, it can make methane, and also from amides where active hydrogens are present. So any molecule having active hydrogen, we can do this reaction. So we will end at this point. One more method is required under alkyl halide. After that, we will see starting from carboxylic acid also how we can make alkane. So we'll end the session here. Thank you for your time.